Reset, test, jump, call and return. Input / output. Basic CPU control. No explicit multiply instructions are available in the original Z80, 33. The registers A and HL can be multiplied by powers of 2 with add A and add HL instructions, similarly 9 and IY also. Shift instructions can also multiply or divide by powers of 2. Different sizes and variants of additions, shifts, and rotates have somewhat differing effects on flags because most of the flag changing properties of the 8080 were copied. However, the parity flag bit P of the 8080, bit 2, is called P/V, parity /overflow, in the Z80 as it serves the additional purpose of a TOS complement overflow indicator, a feature lacking in the 8080. Arithmetic instructions on the Z80 set it to indicate overflow rather than parity, while bitwise instructions still use it as a parity flag. This introduces a subtle incompatibility of the Z80 with code written for the 8080, as the Z80 sometimes indicates signed overflow where the 8080 would indicate parity, possibly causing the logic of some practical 8080 software to fail on Z80.12. This new overflow flag is used for all new Z80 specific 16-bit operations, ADC, SBC, as well as for 8-bit arithmetic operations, while the 16-bit operations inherited from the 8080, add, inc., December, do not affect it. Also, bit 1 of the flag's register, a spare bit on the 8080, is used as a flag, N, that indicates whether the last arithmetic instruction executed was a subtraction or addition. The Z80 version of the DA instruction, decimal adjust accumulator for BCD arithmetic, checks the N flag and behaves accordingly, so a hypothetical subtraction followed later by DAA will yield a different result on an old 8080 than on the Z80. However, this would likely be erroneous code on the 8080, as DAA was defined for addition only on that processor. The Z80 has 6 new LD instructions that can load the D, BC, and SP register pairs from memory, and load memory from these 3 register pairs, unlike the 8080.34, as on the 8080, load instructions do not affect the flags, except for the special purpose I and R register loads. A result of irregular encoding, common with the 8080, is that each of the 8-bit registers can be loaded from themselves, for example LDR. This is effectively a NOP. New block transfer instructions can move up to 64 kilobytes from memory to memory or between memory and I/O peripheral ports. Block instructions ADA and LDDR, load increment / decrement repeat, use HAUTO point to the source address, DA to the destination address, and BC as a byte counter. Bytes are copied from source to destination. The pointers are increment or decremented, and the byte counter is decremented until BC reaches 0. Non-repeating versions LDI and LDD move a single byte and bump the pointers and bit counter, which if it becomes 0 resets the P/V flag. Corresponding memory to I/O instructions in near INDR, OTA, OTDR, INI, IND, OUTI and OUTD operate similarly. The Z80 can input and output any register to an I/O port using register C to designate the port. The 8080 only performs I/O through the accumulator using a direct port address specified in the instruction, a self-modifying code technique I required to use a variable 8080 port address. The last group of block instructions perform a CP compare operation between the byte at HL and the accumulator. A register pair DA is not used. The repeating versions CLR and CPD are only terminate if beep goes to 0 or a match is found. HL is left pointing to the byte after, P or before, CPDR, the matching bit. If no match is found, the Z flag is reset. There are non-repeating versions CPI and CPD. Unlike the 8080, the Z80 can jump to a relative address, junior instead of JP, using assigned date by displacement. Only the 0 and carry flags can be tested for these new 2-byte junior instructions. All 8080 jumps and calls, conditional or not, are 3-byte instructions. A 2-byte instruction specialized for program looping is also new to the Z80, DJNZ. Decrement jump if non-zero, takes assigned date by displacement as an immediate operand. The B register is decremented, and if the result is non-zero program execution jumps relative to PC, the flags remain unaltered. To perform an equivalent loop on an 8080 requires separate decrement and conditional jump to a 2-byte absolute address, instructions, totaling 4 bytes, and the December alters the flag register. The index register, 9/IY, often abbreviated XY, instructions can be useful for accessing data organized in fixed heterogeneous structures, such as records, or at fixed offsets relative a variable base address, as in recursive stack frames, and can also reduce code size by removing the need for multiple short instructions using non-indexed registers. However, although they may save speed in some contexts when compared to long/complex equivalent sequences of simpler operations, they incur a lot of additional CPU time. For example, 19 T states to access one indexed memory location versus as little as 11 to access the same memory using HL and INC to point to the next. Thus, for simple or linear accesses of data, use of 9 and IY tend to be slower and occupy more memory. Still, they may be useful in cases where the main registers are all occupied, by removing the need to save /restore registers. Their officially undocumented 8-bit halves, see below, can be especially useful in this context, for they incur less slowdown than their 16-bit parents. Similarly, instructions for 16-bit additions are not particularly fast, 11 clocks, in the original Z80, being 1 clock slower than in the 8080/8085. Nonetheless, they are about twice as fast as performing the same calculations using 8-bit operations, and equally important, they reduce register usage. It was not uncommon for programmers to poke different offset displacement bytes, which were typically calculated dynamically, into indexed instructions. This is an example of self-modifying code which was regular practice on nearly all early 8-bit processors with non-pipelined execution units. The index registers have a parallel instruction to JP, HL, which is JP, XY. This is often seen in stack-oriented languages like Forth, which at the end of every fourth word, atomic subroutines comprising the language, must jump unconditionally back to their thread interpreter routines. Typically this jump instruction appears many hundreds of times in an application, and using JP, XY, rather than JP thread saves a byte and 2 T states for each occurrence. This naturally makes the index register unavailable for any other use, or else the need to constantly reload it would negate its efficiency. The 10-year newer microcoded Z180 design could initially afford more chip area, permitting a slightly more efficient implementation, using a wider ALU, among other things. Similar things can be said for the Z800, Z280, and Z380. However, it was not until the fully pipelined Z80 was launched in 2001 that those instructions finally became approximately as cycle efficient as it is technically possible to make them. Given the Z80 encodings combined with the capability to do an 8-bit read or write every clock cycle. Undocumented instructions. The index registers, 9 and IY, were intended as flexible 16-bit pointers, enhancing the ability to manipulate memory, stack frames and data structures. Officially, they were treated as 16-bit only. In reality they were implemented as a pair of 8-bit registers, 35, in the same fashion as the HL register, which is accessible either as 16 bits or separately as the high and low registers. The binary of codes, machine language, were identical, but preceded by a new opcode prefix .36. Zilog published the opcodes and related mnemonics for intended functions, but did not document the fact that every opcode that allowed manipulation of the handl registers was equally valid for the 8-bit portions of the 9 and IY registers. For example, the opcode 26H followed by an immediate byte value, LDHN, will load that value into the H register. Preceding this byte instruction with the 9 registers opcode prefix, DD, would instead result in the most significant 8 bits of the 9 register being loaded with that same value. A notable exception to this would be instructions similar to LDH, 9 plus D, which make use of both the HL and 9 or IY registers in the same instruction winking sad smiley 36. In this case the DD prefix is only applied to the 9 plus D portion of the instruction. The halves of the XY registers could also hold operands for 8-bit arithmetic, logical and compare instructions, sparing regular 8-bit registers for other use. The undocumented ability to increment and decrement the upper half of an index register made it easy to expand the range of the normal indexed instructions, without having to resort to the documented add/sbcxyd or add/sbcxybc. There are several other undocumented instructions as well. 37. Undocumented or illegal opcodes are not detected by the Z80 and have various effects, some of which are useful. However, as they are not part of the formal definition of the instruction set, different implementations of the Z80 are not guaranteed, or especially likely, to work the same way for every undocumented opcode. Bugs. The OTDR instruction does not conform to the Z80 documentation. Both the OTDR and OTR instructions are supposed to leave the carry C flag unmodified. The OTR instruction operates correctly. However, during the execution of the OTDR instruction, the carry flag takes the results of a spurious compare between the accumulator, A, and the last output of the OTDR instruction. 38. Example code. Example 1. The following Z80 assembler source code is for a subroutine named hello_world. This is an introductory program which will print a message to the video display and then exit. Example. It demonstrates how an assembler source code is formatted and interacts with the display hardware through a computer operating system. This is necessarily specific to a particular computer hardware operating system and assembler software. The example used is the TRS-80 model for running TOS/ls.6.x, produced by Tandy/Radio Shack and Logical Systems, with most any assembler sold by Radio Shack or Mesosys Incorporated, Series I/ETASM, ALDS, EDAS or MIS with GC switch. The principal features of this configuration are universal to Z80 assemblers, even under CP/M. 3003E69, 3002F, 3003211430, 3006 3E00, 3008F, 3009 0E0D, 300B3E02, 300DF, 300E21000, 3011 3E16, 3013F, 3014 4865 6C6C, 3018 6F2C2077. 301C6F726C64. 3020 21 0D0D. 3023. hello_world_TRS80 model 4. Print hello, world, then exit to Testos ready. Entry registers, none. Return registers, none. Values below are decimal unless suffixed by H. The term pseudo-op means same as assembler directive, is not Z80 code. At CLS EQU 105, EQU pseudo-op sets at CLS text label equals Testos supervisor code. At DSP EQU 2, set at DSP text label equals Testos SVC to send char to display. At DSP LYEQU 10, set at DSP LY text label equals SVC for text string display. At exit EQU 22, set at exit text label equals SVC for returning to Testos ready. ORG 3000H, ORG pseudo-op sets standard start address under Testos 6.x. Start LDA at CLS. CLS equals clear screen, erase display and home cursor. RST40, Z80 restart instruction for system SVC processor, execute at CLS. LDHLMSG, point to message string with HL, required by at DSP LY SVC. LDA at DSP LY, send text string to asterisk do display output device, video screen. RST40, execute at DSP LY SVC, 13D byte needed to terminate string. LDC13, now send another carriage return, needed in Reg C. LDA at DSP, to set off hello message from Testos ready prompt. RST40, once we exit to system. LDHL0, indicate no error condition to command interpreter. LDA at exit, return to Testos ready. RST40, stack integrity maintained.
Yes, I not understand this, because I'm not the computer programmer. I not understand all this code, but I like to read it because that's a part of to understand how the computer processor is working. We call it integrated circuit CPU. This is to understand how a computer is working. Yes. So I just read it and just read the next one. But I just read it later. Maybe I read it when I read it in next year or next years. I will record on video again. Maybe understand more in a few years. Now it's 11. No, I will understand more but I'm not going to. Cannot change to other documents. Then I cannot continue. Yes, let's just continue. Continue.
Might as well have used a ret. MSGDB hello, world, 13. db equals define byte pseudo-op assembles ASCII string to Z80 memory. CRDB 13. 13D byte is ASCII carriage return char, moves cursor down. End start, end pseudo-op required by assembler. To produce transfer record to program entry point. Example 2. The following Z80 assembly source code is for a subroutine named mempy that copies a block of data bytes of a given size from one location to another. Important. The example code does not handle the case where the destination block overlaps the source, a serious limitation, but one that is irrelevant for some applications such as, especially, when the source is in ROM and the destination in RAM, so they can never overlap. The sample code is extremely inefficient, intended to illustrate various instruction types, rather than best practices for speed. The data block is copied 1 byte at a time, and the data movement and looping logic utilizes 16-bit operations. Furthermore, the Z80 has a single instruction that will execute the entire loop.